NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hello, and welcome to another edition of the 2022 Von Karman Talks. I am Nikki Wyrick from JPL's Office of Communications and Education, and I will be your host for our topic this evening, Spacecraft Assembly, Test, and Launch Operations. Getting spacecraft ready for launch requires an extensive team, tons of flexibility, and some serious dedication. Tonight we will look at how the Assembly, Test, and Launch Operations, or ATLO team, come together to assemble it, bake it, shake it, get it to the pad, and launch it. Joining us as co-host this evening is Brian White from JPL's Office of Communications and Education. Hiya, Brian.
Hiya, Nikki. Thanks for having me. Hiya, folks. We just want to remind you that this is your space program, and we want you to be involved in this conversation. So whatever you're watching it on, there should be a chat box. Go ahead and ask your questions in there, and we'll get as many chats as we possibly can in tonight. If you don't see the chat box, go ahead and refresh your page, and it should be right there. Looking forward to this talk about ATLO.
Awesome, Brian. Thank you so much for being here. And to all of you watching, as always, if we do run into any technical difficulties or small failures tonight, we ask for your patience and please stick with us. We'll get them sorted out as soon as we can. Our first speaker this evening joining us is Michelle Colizzi, a mechanical engineer at JPL since 2015. She currently serves as Group Supervisor for the Mechanisms and Mobility Group in the Spacecraft Mechanical Engineering section. Previously, she was the mechanical lead for the Psyche ATLO team and was a member of the Mars 2020 ATLO team. And prior to joining JPL, Michelle worked at Applied Instrument Technologies, where she served as a project and R&D engineer. She was also a part-time instructor at California State Polytechnic University, Pomona, where she also earned her Bachelor of Science and her Master of Science in Mechanical Engineering. Hi, Michelle. Thanks so much for joining us this evening.
Thank you, Nikki. I'm glad to be here tonight with you guys.
Oh, we are so glad you're here. So tell us, what is ATLO?
Yeah, so ATLO, like you said, it's assembly, test, and launch operations. It's where all of the piece parts and components of a spacecraft actually come together to get assembled to create the spacecraft. It consists of a team of various disciplines from all fields of engineering. We've got mechanical engineers, mechanical technicians, electrical engineers, system engineers, propulsion engineers, thermal engineers, hardware quality assurance, system safety, occupational safety. I mean, you name it. We've got a wide variety of people that all serve a very unique and important role as part of the team. So not only do we just assemble the spacecraft, but we also test the spacecraft both functionally as well as environments. We're responsible for transporting the spacecraft. If we can actually show photo 7, all of the ground transports that we do to move the spacecraft from one building to the next for different integration operations, different testing operations. We are responsible for the hardware safety, the movement of it, maintaining the cleanliness of it, and actually executing the test. So if we can show slide 5, please. Yeah, so this was an example of one of the recent tests that we did in a thermal chamber. All of the disciplines are involved in these various phases of the test. The planning, the writing of the instructional procedures, as well as the physical execution, the integration operations for the piece parts that get installed on the spacecraft that are critical to these tests. We have to take all of those considerations into account, especially since most of the members on the team were not the original designers of the individual components. So it's a lot of interaction with those engineers who designed it, making sure we take care and are doing the hardware justice, having all of the safety considerations, because we want this to come together as seamlessly as possible to do what it's meant to do in space.
That is great. Can you tell us a little bit more, like what are the mechanics side of ATLO?
Yeah, so if we can actually flip to slide 2. With the mechanics, so a lot of us work primarily in a clean room. This is actually a prime example. On Mars 2020, we were in full bunny suits. we have to maintain that cleanliness in the facility when we're working directly with the hardware. There's also a number of folks like our systems engineering team who do come onto the floor from time to time, but they support us on console for a lot of the functional tests. So this was actually a very interactive test that we did here, which was showing the deployment of the sky crane maneuver by manually operating a crane, which actually a lot of us are trained to do in the ATLO environment. I had never in a million years thought growing up that I would be calling a crane operation, let alone with spacecraft hardware. And that's something that becomes nearly a daily activity for us there. We've got, and it is definitely a production. You have to rely and trust the team that works with you to be able to execute it, because no single person can do it on their own. Everyone plays an absolutely critical part, and we couldn't be successful if we all didn't give it 100% effort, really show that passion and that care to what we do, and attention to detail, both big and small.
So that's great to hear a little bit about the mechanics. And you mentioned the team. So what does a normal day look like, and who kind of makes up these teams that do all this work?
Yeah, so a normal day, it's an early start for us. We typically get together around 7 o'clock, and we look at a tactical planning. So the leads of all of the disciplines, as well as the ATLO lead, we pull up our schedule for the day, and it shows all of the activities that we want to accomplish on a daily basis, with even half shift goals, full shift goals, a couple days out, and we look at about a 7-day outlook. We also meet twice a week, and we typically do strategic planning, where we look more at big picture. We understand when hardware deliverables are coming in, what the order of operations are, and then we execute. So then after we have our tactical planning meeting, we then start to gather in our groups of our own disciplines. So I would lead mechanical meetings, let's say on Psyche as the mechanical lead. And we then brief the team, who would do a lot of the actual hands-on execution on the floor, what the priorities are, what the nice to haves that day were, what the operations are for the next day, how to start planning, if they can get ahead in areas, what areas to take advantage of. But you have to be very flexible. So really identifying what those priorities are early on in the day are very pivotal. And then after that, we dismiss, and people go and they get the hardware out on the floor. They pull out their procedures for the work that they're going to do, whether it's an integration operation, a testing operation, a transport operation. And then they work with the crew that's on the floor, the technicians, the quality assurance, and sometimes system safety, to make sure that those goals are met. If there is a problem that arises on the floor, no matter how large or small, they immediately notify the rest of the team. You have to be very proactive, but also very reactive while doing this work on the floor. So although we have some milestones, there's a lot of wiggle room in terms of hour by hour basis. So we have to be flexible. Although you say, hey, number 1 priority, number 2 priority, there's many times where we flip number 2 ahead of number 1. Still get both done, but you have to be on your toes and prepared for whatever the day may lead to.
Thank you for that, Michelle. I mean, it's a great look at ATLO in general, and you've mentioned some of the teams. I want to come back to you in just a minute, but I want to introduce our second speaker to talk a little bit more about this. So our second speaker this evening is Luis Dominguez, a system integration and test engineer at JPL since November of 2007. In 2017 and 2019, he was named as one of the 20 most influential Latinos in tech by CNET and Espanol. He studied mechanical engineering at California State Polytechnic University, Pomona, just like Michelle also studied at the same university. But Luis works in testing the electronics and software of robots that explore space. He's serving as the electrical integration and test lead and deputy systems lead for the Psyche ATLO team. And although he loves technical engineering analysis and programming, his primary drive in his life is helping and inspiring others, especially in his native Los Angeles. So hi, Luis. Thanks for joining us this evening.
Hi, thanks for having me. It's an absolute honor to be on here.
Oh, we are so glad you both are here this evening. So Luis, I know you are on more of the electronic side, Michelle on more of the mechanical side. So tell us, what does electronics and testing look like for you during ATLO?
Yeah, so when we start off, and just like the mechanical team, we start off with a shell of a spacecraft. It's really just a mechanical structure. If you could go to image 10 there, essentially you just got a bare bone spacecraft, and you're going to receive several different boxes and units and different instruments from sometimes all around the world and start mounting these things into the spacecraft. The planning starts from the beginning, right? Right from the proposal stage where they're developing the actual mission. And we come up with this thing called the RECDEL list, which is the receiving and delivery list. And everyone kind of agrees to deliver things at a certain order. And that kind of dictates the overall flow for the integration and test team, the ATLO team overall. And as usual, though, that hardly ever goes to plan. And some things come in early that you expect to come in late, and then sometimes things that are coming in late come in early. And so you have to pivot. You know, that's where the strategic planning and the tactical planning that we go through with the mechanical team and the rest of the other teams on the project and kind of decide how we're going to go along with that flow. Because there's a lot of things that need to come together. You've got software that needs to get developed. And then there is a certain order of operations, right, that you put together this Lego block, right? And so if you get a certain piece of hardware in, you have to sometimes decide not to install it because it'll prohibit you from trying to get something else done a little bit later. Or if you do install it, then you need to remove it and then reinstall it a little bit later. And sometimes things are a little more difficult to get off of the spacecraft once you mount them on. So as these computers are, as these boxes are all getting mounted on the spacecraft and instruments, you can kind of think of a spacecraft as a bunch of computers that all speak a different language each, and you're just trying to get them all to talk to each other and make sure that they're following all the appropriate protocols that have been established for the interfaces that they're going to use to communicate. And then as we're integrating it, we have to make sure that it's going to do its job in space. And so we take it through a series of tests. If we go to image 3, so in image 3, this is kind of the setup for EMI EMC tests where we expose the spacecraft to electromagnetic interference and make sure that all the different boxes that are going to be in there are compatible with each other. You don't think about it sometimes, but the different frequencies that all these boxes work at can sometimes cause interactions that you don't expect. And those interactions can be catastrophic in space. So we got to make sure that everything can talk to each other and that it's not going to interfere with each other. And then that we're not going to interfere with anything on the launch pad. So that's one of the other big tests where we need to make sure that any of the RF emissions that the spacecraft actually gives off aren't going to somehow cause the rocket to self-destruct, because like there's certain frequencies that the rocket has that it will self-destruct itself at, and that's how things are designed. So it's an interesting kind of test. And then if we go to like image 11, we can see that we'll actually put it in a kind of a Faraday cage. So we'll create a giant enclosure that kind of shields the spacecraft from the rest of the environment. And we can actually get closer to those EMI and EMC tests that we want to see and make sure that we're not over certain levels and things like that. And then we'll take it to TVAC, which is if we go to image 5, Michelle kind of showed this image a little bit earlier, where, this is the Psyche spacecraft where we actually had, our TVAC chamber is capable of simulating the sun, right? And we've used it for countless missions at JPL. But for Psyche, we actually had to build a toaster oven slash cooling slash refrigerator or freezer to kind of be able to simulate cooling and heating all the different sides of the spacecraft to make sure that the spacecraft's going to do what it needs to do when it's in space, and that all the materials that are on it aren't going to start falling apart, because space is an interesting place because you don't have you're in a vacuum, right? And so things start outgassing that you don't expect, and materials can actually start falling apart. So it's a it's a great little test for the spacecraft there. And then we go into a dynamics test campaign, and we also do all sorts of different tests. So if we go to image 12, we can see this is a solar array deployment test where we actually deploy the solar arrays here on Earth to make sure that they're going to work in space. And in order to do that, you actually have to build this giant structure that Michelle's team pulls together to actually offload the weight from the solar arrays, because they're designed to deploy in space. They're not designed to deploy here on Earth. They would fall apart basically off their own weight if we didn't build this giant fixture. And we do a series of other tests. The next slide 13, shows our spin table test, so where we actually spin it to get the mass properties of the spacecraft. And so that's a very important test, and it gives us a lot of information. And then once we've done all these environmental tests, we move on to transporting the spacecraft, right? So image 14 will show the spacecraft essentially packaged up and ready to go. And that's me saying goodbye to JPL as we left to Florida recently for Psyche. And then back at, we have to take it apart usually when we ship it out, because, you usually can't ship the whole spacecraft as one whole unit. And sometimes you need to send parts out to go get reworked or get some additional work done to them, because through testing you found that they didn't work. But at some point, if you go to image 15, once you got the spacecraft all packaged up, you get the opportunity to encapsulate it, right? And as you encapsulate it, this is essentially the last time you'll see the spacecraft. It's a little different for 2020. We actually had to integrate the radioactive thermonuclear generator, so it wasn't the last time we'd see it. There were little doors there for us to integrate that generator. But we once we've encapsulated, we put it onto the rocket. So image 16. And as you said, we've shaken it, we've baked it, and now we're ready to launch it. So image 17, we'll show you what that more or less looks like. And it takes a giant team to pull this together. As Michelle said, we all work together. It's not, it's not easy, and mistakes will get made, but we get through them as a team, and we pull it together and get the job done. So yeah.
I mean, you said it yourself, teamwork, right? Both you and Michelle have brought that up so much. So let's bring Michelle back into the conversation so you both can team up for this next question. We want to hear about some of the challenges, or as you said, the opportunities for flexibility in ATLO. So Michelle, let's jump off with you. Tell me about some of those opportunities for flexibility in ATLO.
Yeah, so we try and be as proactive as we can, as early as we can. So we have the tactical schedule, we have our strategic schedule. So looking short term, looking at long term. It's really a guideline overall, because there's so many things that are changing on a sometimes hourly basis, where we're short a fastener, we can't proceed with this installation, we need to go and find something. Or someone called off sick today and they were pivotal in this operation, and we don't feel comfortable moving forward until we get them back. So we really have to stay on our toes, rely very heavily on each other to really have that transparency and openness and honesty with each other as well. Where if we're not comfortable doing something, if we say, hey, the paperwork isn't as refined as it needs to be, I don't want to risk it. Everyone really has an appreciation, and that's something that is really hard to find, but everyone has this sense of ownership, appreciation, and passion for what we do, that the last thing we want to do is not be fully prepared to do an operation, still proceed with it, and possibly mess it up. So we're really flexible. We pay so much attention to detail. We want to make sure that we have all of our ducks in a row before we actually start executing something, because we all know what's at stake. And with the ATLO schedule, right, as deliveries come to us later and later, because they face their own, like, certain pieces of hardware overcome their own issues in their subassembly level testing. So not only do they fabricate, they assemble, they test it, then they hand it over to ATLO, and then we do things at a more system or spacecraft level or smaller subassembly level. But a lot of times they identify some issues with the hardware before it comes to us, which is exactly why we test it at that level before testing it at a spacecraft level. So sometimes it takes a little bit longer for them to rework and debug these issues, so that when they deliver it to us, it's in the most confident and comfortable and perfect state that they feel that it is ready to do what it needs to do. And so sometimes that isn't on the day that was originally on either our tactical or our strategic schedule. So we need to, like Luis said, reshuffle things around, make sure that we still have access to get to that part if it comes in late. But also being mindful that our schedule does get compressed when this hardware gets delivered later and later to us. We can't just move launch dates out a couple weeks here and there, especially with the planetary launches. You've got only a certain time within a certain year count before your next opportunity that you have to hit. So it's a lot of just constant rejuggling and reshuffling of the activities, while still maintaining the big picture goals, making sure that you're not doing anything out of order where you're setting yourself up for failure, but still maintaining constant momentum across the whole team to be able to get things done.
That sounds very complicated, and we are all glad you do the work. But Luis, tell me about some of the opportunities for flexibility that you get a chance to deal with in Atlo.
Yeah, I mean, Atlo's fun, but it's brutal. You know, it takes a toll on you. You're constantly have to be on your toes, and just at the top of your game. And as Michelle said, you know, if you're not feeling up to it, you know, it's just, you know, you have to be willing to say it yourself, like I can't come in today. I can't do this today. So, you know, we need I need to take a break, and it's okay to do that. You know, we have a big team, and we usually have people who can come in and fill in for you, and so you know, we're constantly juggling people around, but sometimes, as Michelle said, you need someone who's critical for the operation, or you know, you need to for some cases you need to do specialized testing, like you'll need to use a radiation source, or you'll need to use you know, create a little vacuum chamber. For example, for our GRNS instrument, we have to basically create a little vacuum chamber around it and get that set up, and then that needs to pump down for several days, and we need to support it, you know, on a 24-hour basis for several days as it's pumping down to achieve the vacuum. That way we can actually test out um, bringing a radiation source to it, and someone, you know, will come bring that radiation source and you know, bring it near the instrument, and then the instrument will detect the gamma rays, and then, you know, we had spent 3 days, you know, in a essentially creating this little vacuum chamber. So it's tough, you know, but you know, overall the team loves it, and the team you know, does a great job of pulling it together.
Yeah, you do some amazing teamwork to get this stuff done. And I mean, we've even talked about the fact that you have to create specialized tools to do certain things, that, you know, you have to travel across state lines to transport this stuff. And so the work you do is really great. And I'm sure that the audience has been really keyed into what you're talking about and has a ton of great questions. So, Brian, tell us, what are they asking out there?
Oh, there's so many great questions. It's going to be hard to get to all of them tonight. But somebody on YouTube wants to know, and maybe Luis, you can start with this, because you kind of just were talking about it a little bit. With hardware getting more and more advanced, how do you test for more of these extreme conditions that it might experience?
Yeah, absolutely. And like I said, we have to get creative with it. Literally, the instrument team that delivered the GRNS instrument to us delivered essentially a portable little vacuum chamber that they could wrap around the instrument, while not having to expose the whole spacecraft to a vacuum chamber. Because, you know, for that we need to use our giant 25-foot vacuum chamber. And to run that vacuum chamber, it takes a lot. It takes a lot of time to pump down. You're looking at about 2 or 3 days just to pump down to the vacuum, to a vacuum level. And even then, we wouldn't be able to achieve the level that we need for that actual instrument. So even when we brought the spacecraft into that large vacuum chamber, we actually had to use the smaller, like, portable vacuum chamber around the instrument to bring it down to those lower levels. So it gets harder, and it's sometimes, you know, it's dangerous. Sometimes you're dealing with radiation sources, right? Like the radioactive thermonuclear generator. When we practiced several times integrating that thing as a team. You know, it's a mechanical and electrical operation, and we practice. You know, someone would literally go in with one wrench, start bolting something down, and then they have to practice stepping away, because you want to limit your exposure levels, right? You want to make sure that everyone stays safe and within you know, acceptable exposure limits. And we understand that, you know, we're standing next to a fissile material there, and we're working next to it. But you know, it's kind of cool. It's kind of cool feeling the heat from a thermonuclear generator as you're kind of working on it.
All right. Well, Hayden on YouTube asks, and Michelle, let's say this one's for you. For someone that perhaps wanted to get into integration and testing in Atlo, how much opportunity is there for innovation and design with the new stuff?
Yeah, so there's a ton of opportunities, and really what's character building is a lot of us have built and delivered hardware, so you get that sense of appreciation and technical insight as to how hardware is designed, what it's intended to do, solving a lot of those technical problems. And typically that is a gateway into being on the floor during integration and test, where you don't have a lot of the continuity early on, since you weren't necessarily involved in the design of that specific piece of hardware you're integrating. So you really build a lot of your previous technical experience and engineering intuition that you develop with the more items that you touch. And like the previous question had asked, it becomes more and more complex with the more complex missions that we're doing. So we are always trying to adapt. If we can actually show slide 4, this is something that I think is going to be really, really, really telling, is that every single operation that we do in Atlo with the flight hardware takes literally an entire crew of design engineers and technicians to assemble what we call ground support equipment, both mechanical and electrical. And without that, we really couldn't do anything. So there is a huge aspect of accommodation just to let us have the opportunity to test, to move things around. Like here we have the Mars 2020 aeroshell that we were preparing to move off of a rotational fixture that our ground support team designed. They designed all of the crane lift fixtures to be able to move and transport this thing. And so there's a lot of thought there that we are constantly working to improve on, constantly redesigning for every project, because we have, let's say, a different launch vehicle interface. Sometimes we launch on a Falcon Heavy, sometimes we launch on a Falcon 9, sometimes we launch on an Atlas. So a lot of those interfaces change, a lot of the masses change, a lot of the box footprints change. So we are always having to adapt at various levels to be able to accommodate and actually do the spacecraft justice to meet our testing and integration goals. So it really does take a lot of people with a lot of experience, a lot of out of the box thinking, trying to problem solve both issues big and small. Like, how are we going to get a wrench in between these two pieces of hardware to torque this bolt where all of our standard conventional tools won't fit? So it's a lot of innovation, both big and small, sometimes for the smallest tasks, but overall, just the logistical planning to actually execute is sometimes even greater than scope than some of the actual flight integration tasks themselves.
You answered somebody else's question too. They were asking if that's harder to design these tests than it is sometimes to build the spacecraft. Luis, this one's for you. Jordan on LinkedIn asks, is machine learning used to save simulation costs? I'm guessing running programs and kind of testing it through the computer before you actually test the spacecraft.
Yeah, absolutely. So for Mars 2020, we did a lot of closed loop simulations on the actual flight vehicle. And we did a couple of closed loop simulation tests with the actual flight hardware. And that's really just to characterize the response of the hardware itself. But the bulk of the testing is actually done using Monte Carlo simulations. And I would imagine that they're starting to use more machine learning techniques to try and make those Monte Carlo simulations go a little bit faster and a little bit better. But overall, the EDL team does a great job of running all of those. And by the time we get to Atlo, we're really just characterizing the response of a thruster when we send a command to fire that thruster. How quickly does the computer respond? How quickly does the motor controller respond? And so we can get all those little timing deltas so that they can further fine-tune their simulations and their test campaign.
Wonderful. I'm going to combine these two questions because I think they kind of go together. Both from LinkedIn, though. And somebody asked, what are the factors that affect the quality of materials used in space? And a follow-up to that, would dings to the body of the spacecraft be a significant issue? So Michelle, let's start with you.
Yeah, so starting off with the dings, yes, absolutely. It absolutely warrants what we call a problem failure report, right? And what we do is that is a piece of documentation that we typically use to identify an issue. And then we do an assessment after that. So it depends, what is the size of the ding? Where is the ding located? What material is the ding? What are the temperature cycles that piece of hardware with the ding is going to see? Is that going to have any structural impact to the overall success of the hardware? So you bring in a team of analysts who go through the stress analysis again. We talk with the cognizant engineer. We look at all the interacting pieces of hardware. You look at the load path. So you break it down to very fundamentals to see, hey, is this going to require one of two paths? Is it rework, or is it a use as is? Or is it something where it's so critical that we have to scrap it and pull our flight spare unit and reintegrate that? So it's very circumstantial, but absolutely, as soon as something's noticed, as soon as someone, sometimes even a tool, you're torquing a tool and your hand slips and the wrench can hit something. I mean, that it happens. Mistakes happen on the floor, and it's no one's fault. You have to always just support each other on the team, because the more time and more exposure you have there, something's bound to happen. And it's really how you come out of it and recover as an individual, as a team, and then work the technical due diligence to make sure that that is acceptable, or take the right path to reconcile it if it's not.
Wonderful. Luis, you have any follow-up with that too?
Yeah, no, I'm just going along with, like, sometimes using a tool, you'll do a ding or something, or you'll drop a tool. It's very important as the Atlo team, like, and we always share this with the team, that be upfront and let us know when something happens. Let us know when you see an issue. Let us know if you've made a mistake, because those, even though you might not think it's a mistake, you stood up all of a sudden and you hit some piece of instrument. Let QA know, let everyone know what happened, and then we can make the assessment of whether there's an issue here or not. That way, it's clear and it's upfront. And sometimes in Atlo, and when you make a mistake, you come out and you feel really crummy. It's Atlo gives you some of the best days of your life, and it also gives you some of the worst days of your life.
I imagine that would be true. I think we might have some images for this one. People are asking, how do you get the spacecraft to the launch site? How do you get them to these other places?
Yeah, so I will take this one. If we can go to slide 8. So a lot of times our spacecraft is so large that we require aircraft support to take it across country. A lot of times historically, it's been driven across country with a convoy. But what that does is it gives a lot of exposure for the spacecraft itself to be out in the environment, although it's in a controlled shipping container. I mean, there's vibration from the road, although you take considerations for like an air ride suspension with your truck. But in order to transport, let's say from JPL to Cape Canaveral, which we do very often, we lately have been relying very heavily on air transport with the use of a C-17. So if we can actually show slide 9 as well, it really takes a large portion of our Atlo team to support these operations. And we work hand in hand with the Air Force to actually execute them, because the Air Force is who's actually running the C-17. Their loadmaster works hand in hand with our lead of the operation, and they winch these shipping containers up into the back of the C-17. They make sure things are strapped down. With some of our sensitive hardware, I mean, we have to maintain, let's say, a super clean environment for some of our instruments, where we have to maintain a constant nitrogen purge to, let's say, keep optics clean. And we have to manage that during either a truck convoy or during air transport. So there's a whole lot of planning and consideration that goes into this. And to the point where it's almost a full-time job for a specific individual on the Atlo team to really take ownership of all of the ground transports from building to building, as well as the air transport. There's a ton of permits for the road going from JPL to get to an Air Force base to even load it onto a C-17. So it's definitely a lot of work. It takes a lot of planning, and we do it with essentially the same amount of care we take when integrating an instrument. Every I needs to be dotted, every T needs to be crossed, because there's just so much at stake, and we're constantly reminded of that. And so even just wheeling it out, right? We want to make sure we're doing it slow and in a controlled way, so that we don't have a runaway spacecraft rolling down the ramp of a C-17.
There are so many great questions on here, and I want to let you all know, thank you for asking so many wonderful questions. We've only got time for a few more. On YouTube, they want to know, how do you keep the clean room spaces organized so there's enough room to fit all the big projects? Some of those photos look really crowded.
I'll let Michelle handle that one. That one's it's a delicate dance.
Yeah, so short answer, label makers. Um, we label everything so that we know where it is. There's a place for everything, and everything has its place. And that's almost the beginning of every day and the end of every day. We make sure every tool is put back so that the next user can find it, because we share tools amongst the clusters of us that are working in that space. Not everyone has their own dedicated toolbox. Not everyone has their own dedicated torque wrench, or their own dedicated workstation that stays and lives in that clean room. So it definitely takes a lot. There's a lot of reshuffling depending on what hardware comes in, what's next to go underneath the crane. So if you notice, if we actually go back to, let's say, slide 4, a lot of our scaffolding is on casters, and we have jacks that we can raise the scaffolding on to get them off the casters when someone needs to stand on them. But then when it's time to move them, they're very modular by design. So you can lower the jacks down, get back on the casters. And if we need to roll the scaffolding, let's say to the other side of the room to make way for another piece of hardware, or to make way for a scissor lift to get a technician up, we have that flexibility to do so. But we are constantly modeling in our CAD. We have a CAD of the spacecraft facility in and of itself with the floor plan. And we are constantly modeling at this phase, this is what we expect to have. This is the support equipment we expect to have, the flight hardware. This is the test equipment that's going to come in, and find out a way to make that work where we have our doors cleared for personnel access, or if we're expecting a big delivery, we need to constantly have we have a baseline plan, very much so like the actual activity planning, a baseline plan of where everything should go. And really you have to be reactive on the fly that, hey, this may not work, or we think we need a little bit more space here. We then stop all the operations and get the team, and we're moving things around. So you have a plan in mind. There are slight deviations, but it is absolutely a lot of reshuffling, especially as our missions get larger and larger.
Wonderful. So many great. Okay, we've got time for 2 more. This first one will be for both of you, but we'll start with Luis on this. How long do you begin preparing in advance for a launch? And also, how long does it, the main $1 million question, how long does it take to build a spacecraft?
So typically you start planning for Atlo right from the beginning. So like I said, the moment the proposal's written for how this mission is going to go, they've already got a plan on how Atlo will be achieved. And you're typically looking for most Atlo campaigns a 1 to 2 year time frame. And it really depends on the hardware delivery, how early you're expecting hardware to get in, and how quickly you can have the software ready to test that hardware. For 2020, that one was about an 18-month campaign, I believe. And for Psyche, we're probably about similar, about an 18-month campaign as well, in terms of assembly, test, and launch operations for just Atlo. But it can vary. I mean, some campaigns can probably have longer ones.
Yeah. Michelle, how long does it
Absolutely.
take to build a spacecraft? Yeah.
I mean, it varies on the complexity of the spacecraft. It varies too on a lot of the delineation between what happens at the subsystem phase versus when things are finally delivered to us to Atlo. So a lot of times with the core structure, right, you have there are opportunities where that team had subcontracts with either other groups on lab or with third-party commercial vendors to provide like an electronics box, or provide some onboard propulsion or something of that nature, where they integrate to a certain extent before it gets to Atlo. So it varies so much project by project. But really the traditional, Atlo timeline that Luis was referring to, over an 18-month to about 2-year time frame, is really what it takes. And it's not just all serially, you build it once and it's done. It also maintains a lot of, okay, we're going to put a lot of things on, we're going to go and test. Now we have to take a lot of things off and reconfigure and ship, and then reinstall it at the Cape. So it's a lot of deviation and reshuffling. Once again, it seems to be a very common theme in Atlo. But reshuffling of the hardware on and off, making sure that you're recording the number of cycles that you do that, because that is very important. We don't want to take things off and put things on too many times to where we start to wear some of the main features of the structural kind of bond of that equipment. But we also want to be mindful that the first time you put it on, you with full intention, you may want it to be the last time, but there are very often circumstances where it comes on and off. So you need to maintain that margin in your plan for flexibility for the planned, the unplanned, and the recovery if something goes very far unaccording to plan.
All right, time for our last question, and I'll throw it back to Nikki. On YouTube, they want to know if they wanted to get into this field, would you, both of you, recommend mechanical engineering, astronautical engineering? What would you recommend to do what you do today? How about Luis, you give us a start?
Yeah. Oh, sure. Yeah. All right. I would, so I studied mechanical engineering, but I kind of ended up falling into electronics as an intern. I worked with the electrical team on the Mars Science Laboratory ATLO team, and that kind of helped me develop a love for electronics. So I wish I had studied electrical engineering, but what I ended up doing is, the mechanical engineering and electrical engineering, the math is all the same. The formulas change a little bit, but overall the mathematical principles are the same. And so it's really about just, taking the time. And the great thing here at JPL is we have, some of the subject matter experts, of all around the world that you can go and ask about these questions about electronics, right? I could go talk to someone who's an expert in field effect transistors, right? When I was learning what a FET was, and I could, they could talk to me in detail about all these different things. And it just, further kind of helped me learn about electronics, even though I didn't study electrical engineering. But I would have studied electrical. I wish I had, but hey, you can always learn on the job.
Yeah, and building off of that, always learning on the job. My personal opinion, I think engineering school teaches you how to think like an engineer, and the discipline is really an extra, right? It's based on your list. And do I want to focus more on aerospace, or do I want to, with a mechanical major, we learn a little bit of electrical, we learn a little bit of aerospace, and you have a lot more versatility that way. But at the same time, too, getting a degree in engineering really teaches you how to break things down, to problem solve in a logical manner. And it gives you a lot of the fundamentals with your calculus, like what Luis was saying, with your physics, no matter which flavor of engineering you choose to do. So I don't think that there's one specific major that is the right major to do this job. I think it's really what you make of it and what your interests are. But any of those majors will give you the right skill set to logically problem solve and break things down into the fundamentals, right? Where all of them, you learn how to draw a free body diagram and say, okay, this is where your forces are, and this is how it's going to react. And it's a lot of physics and math that all come together and teach you how to think. And that problem solving is really what makes you successful on the floor. And you get that experience working with hardware, whether it's testing hardware, whether it's building hardware, whether it's designing hardware, whether it's accommodating hardware, right? You build that experience on the job to do the specific task that you're tasked with doing, because no real major is going to train you how to ATLO, really.
That's some great advice that you're passing on to the next generation. And before we end this evening, I know we said that was our last question, but Michelle and Luis wanted to share some final words with our audience. So Michelle, I'm going to throw it back to you. Why don't you start for us?
Yeah, so actually building a lot on that conversation, right? I came from, I'm very local, Southern California, born and raised. I've driven by JPL time and time again growing up on my way to other SoCal destinations. And when I started working at JPL, I'm going to be honest with you, this isn't something I share often, but I had what we call the imposter syndrome, right? We have subject matter experts from all over the world. We've got like some of the leading tribologists who specialize in bearings that were in the same mechanisms group that I was in. And I said, what am I doing here? One day they're going to find out, they're going to catch on that I'm a fluke. And my career path has not really been wanting to go and be that subject matter expert. And I found that people of all backgrounds have a place in aerospace building flight hardware, whether it's supporting in INT, whether it's designing, whether it's building facilities and infrastructure, or testing rocks in the Mars yard, or doing the science. I mean, it all is so important, and there's no one path to get there. So I really found that niche that, hey, I can play off my skill set of being resourceful, being a good communicator, really wanting to solve problems, and knowing when I am not the person to provide that answer, going to find the right person to provide that answer. And that's a skill set that not a lot of people necessarily have. And that's it's very different, because I am not a subject matter expert. I am probably a jack of many trades, but a master of none. And that does contrast with a lot of the subject matter experts who have the answers, but they don't always have the answers for everything. And so, kind of summarizing all of that, the biggest takeaway is I want everyone to feel encouraged that if you are passionate enough and you want to pursue a career in aerospace, and you want to do ATLO, or you want to go and design like the next rocket, there is no one path to get there. It's really based on your experiences. It's what you make of it. It's maintaining that motivation and drive and confidence in yourself to reach and achieve your goals. Because if you try hard enough, like one way or another, you will get there. It's just maintaining that motivation and morale to accomplish those goals.
I certainly feel motivated. Thank you for those words, Michelle. And Luis, I want to pass it off to you for your final words.
Yeah, absolutely. Yeah. And you know, I was always passionate about airplanes. I always wanted to work on airplanes. Growing up, my first love was airplanes. And I chose mechanical engineering only because my dad was a mechanic. And so I understood mechanisms, I understood cars, and so mechanical engineering seemed very natural to me. You know, I had never thought of electrical engineering as a potential career path. But once I got here at JPL, you know, I was just given a lot of support and a lot of help to kind of develop those skills. And so what I would say is, you know, just, you know, keep developing those skills, keep developing different skill sets. You know, at every opportunity, take a chance to learn anything you can, because, you know, any additional skill you learn is just another tool that you can add to your tool belt. You know, what I always tell my when I do outreach to kids is, you know, live your life with courage, curiosity, tenacity, and a healthy dose of altruism. You know, and if you're doing those four things, it doesn't matter where you're at, it doesn't matter what you're doing. You know, you will succeed, and the people around you will succeed. So, yeah, those would be my parting words.
Those are some pretty impactful words from both of you. So, unfortunately, that is all the time we have for today. I want to thank our wonderful speakers this evening, Michelle Colizzi and Luis Dominguez, for joining us to discuss spacecraft ATLO. Also, a big thank you to our questions co-host, Brian White, and everyone working behind the scenes to make this possible. And to all of you watching at home, thank you so much for taking time to join us every month. If you missed one or would like to revisit any of the Von Karman talks from the past 5 years, they are available on JPL's YouTube page. And please do join us next month for Curiosity, a Decade on Mars, where we will dive deeper into what the Curiosity rover has done in the last 10 years on Mars. Thanks, everyone, and have a wonderful evening. Bye.